Hello. Hello. Am I audible, madam?
Yes, yes, I can hear you. Can you hear
Oh,
me?
yes. I am able to hear you. Madam, can
Okay.
we wait for 2 minutes so that the participant can join? Then we can start the session.
Yes, yes, sure, please. Yeah.
So this is the 6 o'clock. The session will start already in 6 o'clock, but the participant will join soon. We can wait for 5 minutes, and I will introduce.
Yeah. Then we can start. Sure, sure. No
Yes.
problem.
Okay.
Okay.
Thank you. Okay, so I welcome to all these participants for the day 5 session today, because this FDB program at IIT Guwahati, today is the day 5 session. We are started. So just all of you, please be pay your attention for today's sessions. So our first session speaker is from industry. That is our speaker, Madam Ms. Seema Nagar. She already has joined the sessions. So just I will quickly introduce to Madam from our participant background and participant side. Then also I will introduce Madam to our participant also. So, Madam, from our participants are mostly the faculty members, research scholars, and the master students across the India, various institutions. They have joined from various background, mechanical engineering, civil engineering, science, and other stuffs of engineering fields. They joined this program. More than 100 participants probably joined today's sessions. We expect that. And also I will introduce today's speaker to our participants. On our sessions, first start with our speaker, Ms. Seema Nagar, is an industry person. She is a senior research scientist at IBM Research India with over 18 years of experience in computer science. She has authored of more than 45 publications, field of 150 plus patents, and is in 3 times IBM Masters Inventor. Her work, social network analysis and trustworthy AI, and the AIOPS has earned her multiple research awards, including the 4 outstanding technical achievement awards. Also, Madam is also an active mentor and reviewer for top conferences such as IJCAI, NAACL, IEEE Cloud, and ACL, and many more. So just I welcome Madam to our sessions, and and also I expect that all the participants will learn a lot of information from your side. You please start your session. I hand over to you. Thank you.
Okay, great. Thank you so much. Thank you for the introduction. So let me start. I'll share my screen. Please let
Yes.
me know if it's visible. Okay. So yeah, let me share my screen. Can you see my screen?
Yes, it's visible.
Okay, great. Okay, so let me start then. So today I'm going to talk about a very relevant problem in the industry today, and there is a lot of industry research as well as academic research going on in this domain. So one second, I want to minimize this. Okay, so yeah, so all of us every day we use such as these web portals, right? Amazon.com or your tickets booking portals, ClearTrip, Book My Trip, all of that, right? And what happens behind the scene, right? Under this IT application, there is a distributed microservices based system. And all of these microservices based systems are inherently complex because of there are so many different, there could be hundreds of thousands of microservices in this IT distributed application, right? And we have often heard there are outages, right? Let's say if Amazon.com goes down for a few seconds or for a minute, it is a huge loss for the company, right? And similarly, even for the customers or for the end users or for the society, right? The outages in tech industry has caused a lot of disruption, right? These are very recent examples, say 2024, where uh, outages in cloud has caused delays in the flights, cancelled flights, and passengers got stuck in the airports, right? Here you can see the long queue because people couldn't book the tickets and couldn't board the flights on time because of there was a glitch in the portal. Now, all of so this tells, right, why should we look at uh, health of these applications proactively, right? Before something goes wrong, can we proactively monitor the situation or the health of these applications, these IT applications, which are distributed in nature, so that we can minimize such outages, right? So the majority of my talk will basically illustrate various methods around how can we proactively monitor the situation, these kind of situations, so that we don't have to, so that the end user don't have to suffer or the business don't have to suffer, right? So that is the aim of this presentation. And this whole process is called IT operations. How can we effectively manage IT operations so that the downtime or the outages or the incidents in the IT applications can be reduced or can be minimized? So the IT ops, and now with AI in being useful in every setup, so AI is also useful here, and I'll talk about how AI is being leveraged to critically monitor the health of these IT systems. Please feel free to interrupt if there is any question. Just let me know. Okay, so this is a chart which shows that how the complexity of the software has been going up, right? Initially, we were more like traditional architecture where we were using waterfall kind of software cycle, and then people moved to agile where there were frequent changes to softwares or these IT applications, and slowly people have moved to AI driven IT ops, right? Where AI is being used for the frequent changes in the IT ecosystem, right? In the IT applications. And then with time, these applications have become more complex. And initially, there were more the components of these applications were simple, and they usually were hosted on traditional data center or maybe on a cloud or private cloud or public cloud. And then slowly there are a lot other components being added, which are, let's say, we can have now in the same IT ecosystem, we can have software service, we can have platform as service, we can IoT, edge, other devices. Then now we have quantum computing, all of that, making these IT systems more complex. So if you see, the complexity of the IT system has been consistently going up from 2000 till now, right? So now with the increase in the complexity of these system, that we want the reliability. Everybody want the reliability to be high because system should be reliable. Then only the end users will be able to use it, right? And with that, manageability, since many of these systems are distributed across different clouds or different types of data centers, then manageability becomes anyway hard. So all can we, so the goal here, can we effectively manage the IT operations using the observability data? I'll talk about what are the observability data we have from the IT application and how can we leverage those data modalities for the monitoring of these IT distributed applications. Okay, sorry, I want to, one second, I'm not able to minimize this. My slide is not completely visual. Okay, anyways, yeah. So now, so this is how a typical IT application look like. Uh, it's a microservice based system, and microservice based system is consist of various microservices, and these microservices are usually run on a container, and the container is hosted on a physical node, which is a physical server, right? And from these physical machines, right, we can collect metrics which can tell about the health of that node. The metrics could be resource metrics such as CPU utilization, memory utilization, uh, other bandwidth, etc., right? All of that. And similarly, for the container level, again, we can collect instance metrics So these can be monitored to look at the health of the container. And so this is how the data modalities which can be used, right? The data here, the metrics are the data. Someone is talking. Okay, so there are these. So we have metrics as one data modality, and then what happens in a typical microservice system? We have one microservice calls another microservice. For example, let's say when you log in to Amazon.com, there is a login service. Can we move?
Hello, participant, please mute yourself. During the discussions, you should mute yourself.
Okay, thank you. Okay, so yeah, so now let's say you log into Amazon.com. So first service which is probably being called is login service. So you log in, and now next thing which you do is browse some products, right? So maybe there's another service which is called catalog service is being called, right? So one service calls another service, so that makes there is a caller and there is a callee, so it becomes a pair. And now whenever now this pair is called basically whenever a user logs into the system and whatever he or she does, right, the entire transaction is logged, right? So I logged in, service A is called, then service B is called, then C is called, right? Finally, let's say service A is again called. So that is a transaction, right? This whole path is called a trace. So a pair is called an invocation, a span, which is basically from service A to service B I went. And then the whole transaction that I went to service A, then B, then C, then D is called a trace. And all of these microservices are generating logs, right? Logs are nothing but your print statements or your debug statements, right? Whenever we write program, we put these print statements to debug it or to check what is going on in the program, right? So we have, so from a microservice system, a distributed system, we can collect three types of data modalities. That's what it looks like. So we have metrics, which are resource metrics, and we have log messages, which is basically text. And we also have the traces, how a request is flowing in the system. So one request could go service A to B, then C, D. Another could go A to B, and then B to E. So all those, what are the paths in the system being taken by a request are called traces. So we have three different modalities. Now based on these three different modalities, what can we do to proactively monitor the health of an IT system? Okay, so yeah, so this is why we say there is a multimodal data which is available from the IT system, and we can use this multimodal data for automating some of the IT operations, right? So what we have, what are the various multimodal data available with us which can be leveraged to monitor the health of these applications or to perform IT operations? We have metrics, like I talked about metrics, we have traces, we have logs. Along these three which are emitted at runtime, right, we also have topology, which is basically which service is calling which other service, how the services are connected with each other in a distributed sense, in a distributed manner. So that is the topology of the system. And then we also have alerts. So alerts are nothing but problems which are there, which are being detected in the system. So alerts are nothing but what is the problem? Is the CPU, it could be that CPU utilization is going up. So there could be an alert for that one, right? So those are the alerts. And usually there are IT monitoring tools which has rules written to figure out these problems. Then we have incidents. Incidents could be, like I said, these outages. Outages in incident where many alerts could be grouped together to form an incident. An incident, there is something has happened, right? There's some degradation in the service you can see. So that is an incident. Now then we have Jira issues. There we have code check-ins because these IT applications are continuously being updated, right? With new features, new services, with new deployments, right? So there are continuously with this agile development, there are continuous code check-ins. So we need to also take care of is because of a new code the problem has occurred, right? And then we have deployment data, which is basically your infrastructure, right? Which container the services are running, what are the nodes, the physical service, all of that is comes under the deployment data. So these are the various modalities we have to monitor the health of these distributed IT systems. Okay, so now I will talk about these modalities one by one. So what are metrics? For example, here we have CPU uses, right, over time. So this is what is this is basically numerical number. These are numbers, right? So it's so metrics represent numerical numbers, and these numbers basically tell what is the problem in the system. If I say okay, CPU utilization is is reaching 100%, that means the system is really is clogged now, is overly used. So that is that problem we can figure out from the numbers, from that CPU uses numbers, right? So basically these numerical measurements, they represent what is the system health or what is the performance of the system, right? And these are usually used for, right, for anomaly detection, what is the trend. We can use these numbers for capacity planning. Let's say CPU is constantly going up, memory is going up, your IO is going up, probably you should scale out your system, right? And so that is why these numbers could be used for capacity planning and early warning also. My CPU is going up, now it started going up, I see continuous trend of going up, probably I should raise a warning, right? So that is again a use case for using these numerical measurements, right? So what are the so what are the challenges to figure out these insights from these metrics? We spoke about that an IT system typically comprises of hundreds of microservices. One microservice actually, let's say, is hosted in on one container or probably two containers, right? And those two containers are running on two different physical nodes. So can you imagine the volume of the data, or the now constantly collecting CPU utilization, memory utilization, or any other resource metric? And now all of these metrics you are collecting or storing for each of the service, right? For each node and for each container. So that makes it very high cardinality. Usually these resource metrics are hundreds in numbers, right? And if you see there are 100 services, the number of metrics we have is 100 into 100. So that is a huge number. And then these are continuously being collected. So that makes it even more, the volume becomes very high. So how do we analyze these numbers? How do we proactively figure out that there is some problem? So that is why the high cardinality of these metrics makes it challenging to figure out what is going on in the system. And further, if you measure just one metric, it might not reflect the entire situation, right? You need context because let's say CPU utilization going up, but memory utilization is going down. Maybe there is some other issue versus both of them are going up. Maybe there is some other issue, right? So you need correlation across these multivariate time series, which is basically there are hundreds of metric. For each metric, I have a time series, right? And I need correlations across all of these time series to figure out what is going on in the system. So that is why figuring out or getting insights from these metrics becomes challenging just because of the huge number of metrics and the volume it is being collected. Next comes the logs, right? So what are logs? Logs we all are familiar with. We have written programs and we write these print statements. So let's say somebody logs into Amazon.com, says there might be a print statement which says user A has logged in. Then maybe user B has logged in. Now in this, if you see a variable, the name of the user is a variable, right? Rest of the string is constant. So this is how typical log lines looks like. So they have a variable part and they have a constant part. So we call them, sorry, we call them unstructured, which it could be just pure text or it could be semi-structured. And usually there is a timestamp associated with these logs. And the logs represent what is going on in the system, right? And logs could be generated by the application, by the network devices, and by every component in the system, right? So you have uh, plenty of logs, right, coming from all these components which are present in an IT system. Now, logs tells us why the problem is happening. So let's say there is a database issue because of which a service is calling a database. The service couldn't call the database, right? Now B was calling, this service B was calling the database and A was calling B, right? So since B has failed, A will also fail because A depends on B. But so now how do we figure out? A is also emitting erroneous log messages, B is also emitting erroneous log messages. But who is the culprit? So we know that B's logs will tell, right, what is the problem. B's logs will have that it is not able to connect to the database. That's why there is a problem in the system. So you logs can tell why the problem is happening. So that is why monitoring the logs is very important. It can help us in the root cause analysis, and it helps in the post-mortem investigation, right? It can even help in the auditing part, right? If there is some let's say some attack has happened, maybe you can go through the logs and see what has happened, right? And what sequence of logs has occurred in the system. That tells a lot what is going on in the system. Now we have logs with us, but then what are the challenges to get insights from these logs, right? So first is volume. Logs are huge. The number of log lines generated are huge in number. So if you say, let's say, just take an example, Amazon, maybe terabytes of logs are generated every day. Now imagine analyzing these terabytes of log messages at the pace they are being generated. So that is this volume makes it difficult to get insights. And then there is a variety. Every developer doesn't write logs in the same format. That I have a timestamp, then I have a debug level, then I have the rest of the string, right? So people, every developer has their own choice of writing the logs in a particular format. So there is a variety in the log format. So I know there is a first string is a time, but everybody writes time in a different format. So how do I parse it? So there is a lot of variety which happens because of different people are writing uh, the the code for the IT system, right? For an IT system, that's why there is a variety in the logs. So how do we have a generic parser which can parse all the logs? And then since it's a distributed system, so we need to correlate the logs across all these services, right? Then only something can be said about the root cause, right? Because errors are originating from, let's say there are three services which are showing the errors, but then maybe there was a problem in only one service which was causing that issue. So we need to correlate these logs across these different services. Now comes the traces. So what are the traces? Traces are basically your end-to-end path of a request. So it is usually called a transaction, and basically the request propagates through the system, right? And it will touch upon various services and components in the entire distributed system, right? So here if you see one example, so there is a front end, user logs in, then this calls the gateway service, and the gateway service might call the other services, right? It might call the recommendation service or the product catalog service. So this entire path is basically a trace, a request which the path a request has taken is called a trace. Now trace tells how the problem is happening. Let's say this particular service has some issue, then response from this service will be delayed, right? So that means this will the let's say the response time has gone up. So now the trace will have the response time from here to here, right? So this will tell that the entire trace will tell this is how the problem is happening in the system. Here the response time is going up here first, followed by here, right? So that will tell us how this problem is propagating in the system. Okay, so traces can help in many things, right? It can help us in what are the services, what are the dependencies in services, how can we do the optimization of this system, and let's say how can we do the localization, right? Let's say this service goes down, right? Because of which there is a delay to here, and then finally there is a delay to here, right? So that means using the traces we can localize that this is the main culprit service which is causing the entire problem, right? So through the trace we can figure out what is the fault, right? That is called fault localization. Which component is responsible for the problem or for the fault? So now, what are the challenges associated with traces? Traces are actually, you need to instrument your IT, that service code, right? Whenever a request comes in, we log that this request is coming in from this microservice, and then basically instrumentation is needed. So which is a tedious process. You have to make the changes at the code level, and since if once we start instrumenting, that there could be overhead, right? There is, since there's a code is changed, you can introduce overhead in the system, and stresses the number of requests are huge. That means that the storage is the large volume of stresses are being generated every day. So we storing such a data is itself a challenge, and then analyzing such huge stresses is again another challenge. Okay, with that, let me go to topology. So we have logs, matrix traces, and we also have the topology, which is basically your the map among your services, right? It's a dynamic map in the sense that new services keep getting added, and maybe the services being deleted also. So it keeps updating with time, and this so and the sorry the topology or the just need not have the services, it can have the hardware components, right? The container. So we call it, there's a vertical topology and there is a horizontal topology. The horizontal topology is basically which service is calling which other services, right? The call graph. And while the the vertical topology is which instance, which container service is hosted in, which node and container is hosted in, right? So all of that makes the topology of an IT system. Now this is the topology can really help, right? We can help in figuring out the impact of a problem. Let's a service goes down, we can see, okay, there are these other services which depends on this particular service, so these will also get affected. So I can figure out what could be the impact of a service going down because I have the topology of these services, the relationship between these services. And so we call it blast radius, right? So blast radius is something I can figure out, and that can really help the engineers who are taking care of these systems, right? What it tells that what could be the impact of a problem, right? The severity of a problem. So that can help the site reliability engineers who are taking care of these systems, who are monitoring these systems. They can prioritize the various problems which are happening in the system, right? Now, what are the challenges to analyze this the topology data? We it constantly gets updated with time, right? So it's ever changing, and that's why always getting the topology from an IT system is actually difficult task. It keeps changing. There are new components in the system. You have to constantly update it, and if something gets updated, you have to rerun your analysis. All of that has to be done. That's why topology maintenance itself is a big problem. Now then we have alerts, right? Alerts are, what are the alerts? Alerts are basically these are rules written on, let's say, your metrics or your logs or your traces. So if I see a problem, so there could be threshold based rules that if I see number of erroneous log lines in last 1 minute more than 100, then I will raise an alert that the number of erroneous log lines have gone up. So that could be one alert. And another alert could be, okay, the response time from service A to service B has gone up, right, above a certain threshold. So these are basically base anomalies. Alerts are nothing but we can call them anomalies in the system, and there is usually there are rules written to figure out these alerts, and these alerts can really help the engineers, the site reliability engineers who are taking care of this system. How what are the problems? They can proactively figure out, right, what are the problems in the system, and maybe they can take some intervention even before the problem occurs. For example, see they see that CPU utilization may be beyond 70%. I should raise an alert, and then the site reliability engineer get an alert that okay, there is this issue going on. There is a CPU utilization is going up. Probably I should do something about it, right? So they can proactively take care of the issue which might occur later. Now, what are the how to have effective alerts, right? So, like I said, we usually have a threshold. So these systems usually have a threshold beyond which they say, okay, there is a problem. So beyond a certain threshold in a metric, there is a problem. Beyond a certain threshold in the logs, there is a problem, right? So how do we figure out that threshold? So setting that threshold effectively is a difficult task. So and this is common alert fatigue, which is basically there are so many alerts being raised because there's so many components, right? And we know that one component depends on so many other components. So alert fatigue is a very common issue. There are too many alerts, even, and most of the time these alerts are noisy, and because there is no universal rule that these are the threshold. Probably one system is should have this threshold should be adapted to different systems depending on the environment or the nature of the system, but usually they are not adapted, right? So there is a alert storm is a common problem. So an SRE who is looking at the site reliability engineer who is looking at these alerts gets insane, right? That how should I handle these alerts? So so the main problem is how do we control? How can we group these alerts so that the alert, the volume of the alerts goes down? Then we have incidents, right? So an alert need not always mean a problem. Incidents are actually, we say there is a problem has happened in the system. There is some disruption. There is some service disruption, the degradation of service or something, right? And it requires a proper investigation. So there is a proper team which maintains these incidents, right? These are the incidents which have happened in the past. What was the root cause? How the problem has occurred? Everything is maintained in an incident review, so that they can identify the recurring issues, or they can have a solution if there is something has happened before. They can use the same thing again. Now, how to proactively predict incidents, right? That is a big problem because they see the alerts are coming from different components, and then how do we correlate these alerts together? An incident can have multiple alerts, right? Because service A has gone down, B is also emitting alert, C is also emitting alert, A is anyway maybe not emitting any alert, but then there are so many alerts being generated by these different systems, by the components in the system. We can just figuring out, right, which are the alerts because of the same issue, right? So which group corresponds to one issue, right? There is this group of alerts, I can say they are being generated because of the same issue. Then it becomes easy for the site reliability engineer to fix that issue, or to figure out, to diagnose the issue, or finally figure out the remediation, right? So in an incident, usually the different teams will collaborate to figure out what could be the remediation of that issue. Okay, so what are now these, we have these different observability data coming from the distributed IT systems. What are the other challenges apart from we talked about, right? So we know that these there are different agents collecting these different modalities. So we have logs are being collected by Logstash, metrics are collected by AppDynamics or something else, right? A matrix can be stored in Prometheus, logs in different storage systems. And then we have, since these are coming from different components, the timestamps may not be aligned, right? So that we need to align the timestamps. Then they're measured at different granularity levels, right? Maybe CPU utilization is measured at a different per minute, or maybe your IO throughput is measured at a different level. All of that different granularity levels are existing among the metrics, right? Then there is a diverse data formats. We have logs are our semi-structured text, while metrics are numbers, traces is sort of a graph, right? So we have different data format. And then always this service dependency map, the topology I spoke about, is not available. Usually it's hard to get a topology of a system because of just so many services in the system. So and then topology is usually inferred from the logs or traces. Okay, so what types of insights? I have been talking about what insights can we get from these logs, metrics, traces, or these other data modalities which we can collect from the IT system to finally proactively monitor the health of these IT systems, right? So so we can do anomaly detection from using logs, metric traces. Incident prediction can be done using the alerts, and we can use topology. Fault localization, which is the culprit component, that can be done using alerts, logs, traces, topology, right? Blast radius I spoke about, right? What is the impact of a problem, right? Again, we can use topology or alerts and logs, right? And for root cause analysis, we need a lot of things. We need what are logs, where are the problems happening, how the problems being manifested in the traces. We need deployment data, maybe checking there's a problem in the code which has been just checked in and being deployed. And then at the end of the day, right, once a root cause has been identified for an incident, you need SME, which is subject matter expert, has to be identified because someone has to fix that issue, the incident, right? So again, how to identify that subject matter expert can be done through the check-ins, the code check-ins, who will deploy the data, maybe through the logs and traces. Okay, so these are the, like we spoke about now, right? We have logs, metric, traces, topology. By doing various transformation on this data, we can figure out various insights. We can do anomalies detection, alert grouping, incident prediction, right? So fault localization, SME identification, root cause analysis, right? So all of these are helping in proactively monitoring the health of an IT system, right? Okay, so with that, let me talk about a few approaches of how these IT data, these different modalities of data being used to extract insights, right? So, like we said, right, metrics are basically time series, right? So, time series data, and this is collected maybe at a certain granularity, and we know that different metrics are collected different granularity. So usually first thing which is done is aggregation, right? So we can do aggregation, let's say per minute window, which is, let's take the mean of within that 1 minute window for all the metrics, right? So aggregation is usually done. So that is, and once we have a this representation as a time series, we can do various time series based anomaly detection or time series forecasting. All of that can be done. Similarly, for traces also, they are usually converted into time series, which is basically what is the response time, right? For each trace, what is the end-to-end response time? What is the average response time? So that what is the latency of a service of a trace? So that is a one time series, right? And then error rate could be another time series, count of traces which have been errored, right, in a 1 minute window, let's say. So per minute we have error rate, and then we can also throughput how many number of requests, right? How many requests processed per second per minute for a given service or endpoint. That could be another time series for traces. So why we are doing all of this? Because directly analyzing the raw data is difficult. So we want to convert the raw data to a format which can be further analyzed to get the insights. And how do we analyze the logs? So logs are we can say, okay, from the logs I can filter out the errors or warnings, but errors and warnings, there need not be always problematic, right? There are actually benign errors, warnings which get printed even in a healthy state, right? And sometimes there are no there are no error messages or warning messages present even there is a problem has happened, right? So, and then in order to figure out, right, that how the service has been flowing in the system, what is the transaction flow path. So we need, can we use the logs to figure out what is the trace, right? Since trace is not always available, so people use logs to figure out the trace. So this is some sample of the logs. So we have here, let's say this preparing response for job request equals to some job request, right? And then some port ID, this another log line which says port ID, no waiting. Then again we have the similar log line, right? Preparing response for job request. Now this time the job request has changed. The job request number has changed, right? And then again similar message, right? The job submission message we have port ID has changed, and there's a string no waiting, right? This is same as this one. There's another log message synchronized response for job request equal this and this, right? So what you see, right, that in typically these log messages repeat a lot, meaning that here if we see um, this particular first one, right? So preparing the response for job request equals to this one. Then another, there's one more request of similar nature, right? So can we see, and we know that these log messages are huge in number. Maybe we can group them based on this nature that they are repeating. So this is called a template in the log world. So preparing response for job request, this is one template. Then this port ID no waiting is another template. So this is how usually log messages are compressed from a huge volume to a small volume through clustering. And the clustering is called templatization. That's what is referred here, which is basically finding a template. So I'll give you one example here. So here is, So now we can say this, let's say connection established from, this is the IP address. So connection established from star. So this becomes template, right? So it's template T1. This another template, disk users on web server 01 exceeded 85%, right? So disk users on star exceeded star, right? This is another template. Star means anything can come here, right? So these these two templates are present, and let's say if you want to mine how the sequence of log is coming, right? That can also tell whether there is a problem or not. We know that a particular request should follow this path, but if that request has not followed that path, maybe there is a problem in the system, right? So that one can be figured out also through the logs message sequences. So let's say typically we have that T1 is followed by T2, again T1, T3, right? These are the template IDs. Maybe we can use these sequences as a guiding mechanism to figure out if there's going to be some problem in the future in the system, right? Okay, so so this is how the conversion from the raw data to intermediate representation is done. So metrics are anyway time series. Yeah, just to repeat, metrics are time series anyway. Traces are also converted to time series, and then logs are templatized, clustered, and then we can create time series also for log, which is basically in per minute window. Let's say how many how many log lines are of type T1, how many log lines are of type T, right? So the number of log lines belonging to cluster T1, number of log lines belonging to cluster T2. So per minute, again we can create a time series from the logs, and also we can create sequences from the logs. Okay, so now traditionally, how this, so first thing is template, simple approaches such as, let's say, not repeating, maybe that's a variables, a string will repeat a lot, right? So certain, based on certain statistical nature, we can figure out this is a constant part and this is a repeating part, right? So this is one template. And there are other methods such as drain. Drain is being used popularly a lot. So drain, I'll tell how drain works, is basically works based on a depth. And so there is all of these work based on the occurrence of the number of times these various strings have occurred. And so all of this is what traditionally people have been doing. So they find this template based on these various approaches. And what are the limitation of these traditional approaches? That there's a lot of manual effort, or also it's hard to extend to another format, right? Usually, one log format is what one clustering algorithm will work. Maybe if you want to extend to another log format, you have to change it. And once we have let's mine the logs, right? We anyway have converted logs to log. After that, we can convert logs to time series, metrics to time series, also traces to time series, right? Then we can do anomaly detection, and there could be the G-score, PCA or ARIMA, all of those time series based, right? So ARIMA is a statistical approach to figure out anomalies in a time series, and PCA, we know Z-score is again a deviation, right? So all of these statistical models have been used to figure out the anomalies. Then people have also started some unsupervised way, which is basically clustering. And then there were some supervised approaches using SVM, logistic regression, etc., right? But and what happens? All of this, there is a high false positive rate, because the clustering will not always be there will be changes in the environment, so clustering has to be updated. And G-score, we don't know what G-score, we should keep it. Again, ARIMA is a statistical approach. If there is a change in a time series pattern, that will not be captured, right? So all of those struggle with the high false positive rate. And then they are not able to take care of the multimodal signal, right? One, there is a causal relationship, right? One metric might be affecting the other metric. So if I have to figure out the problem in a system, maybe I need to look at all the signals together. So they don't do, right? All of, so that is a big problem in the traditional approaches. Uh, Very important problem, very important issue to figure out what is the root cause of a problem. So people use dependency in the there are dependency rules, or we can use the causal graphs from the system dependencies, right? But again, they do not generalize, or they are only for a data which they've been trained on. Right? Fault localization, again, people have been using call graphs, service maps, and for incident prediction, which is basically from the alerts can we predict incidents. So again, these are time series forecasting or classical ML approaches, right, have been used. So all these approaches are sort of brittle. They cannot be extended to a different unseen data. So and these approaches don't take care of the multimodality of the data. So all of these approaches struggle with false positives, and they don't always work. So therefore, with these traditional approaches, then after that, research started exploring the deep learning approaches, right? So the one of the famous paper was DeepLog, which was using LSTM to figure out the templates. So it was using Brain only to figure out the templates, but it was using LSTM to model the log sequences and finally figure out the anomalies in the log sequences. Similarly, there have been other papers which were using attention mechanism and other things, CNN, RNN based approaches to figure out the contextual anomalies. And for fault localization, in the era of deep learning, which is still going on, the people started using graph neural networks, right? Which, you can model the dependency graph is anyway graph can be encoded using GNN, right? Graph neural networks, and then use the embeddings to figure out the faulty component and what is the root cause. And then incident prediction also people were using time series forecasting they started using with deep learning approaches, right? LSTMs were being used for the metric prediction, and there were variational autoencoders to detect the unusual pattern. But in the talk, my main focus of this talk is to present the recent approaches, right? And what can we learn from the recent to propose new ideas. So that is the main goals. I will not go in the details of these traditional approaches. I'll more majorly talk about the most recent approaches. Sorry. Okay. Okay. So yeah. So with the now the recently people have started LLM because everybody using these large language models, they are good at reasoning. So people have started using, the researchers have been using LLM based technique to figure out the problems or to figure out the templates, right? For log parsing, so LLMs are being used. LLMs are also being used for root cause analysis, and then graph neural networks and graph transformer networks, right? Both have become popular for anomaly detection and causal reasoning. And then people have also started using few shot, zero shot learning for parsing the heterogeneous logs. And then multimodal fusion, which was not actually totally explored earlier. People have been exploring the multimodal fusion, right? Because without using all the data modalities together, it's hard to figure out what is the root cause of the problem. So logs, metrics, plus stresses together have been used together for figuring out the root causes. That is called multimodal fusion. And so I will now go to few of the recent work in this domain. Recent work use leveraging probably the LLMs or the graph transformer networks. So here is the very recent paper from my group only. And here what we are saying that logs have different format. For example, if you see here, these logs are coming from SSH, right? And you see the date is a different format than logs coming from Hadoop and coming from Spark, and maybe there is a different type of debug level, right? Here there's info, there's no debug level present here. And so basically every log format has its own type of entities. So in this particular work, so we are figuring out what are the various entities, and it's not only for one log type. We wanted to build a generic, a universal parser which can parse these entities from all the log types. So we used LLM, right? And we fine-tuned on few examples from all of these log types, and then that fine-tuned large language model was eventually used to figure out these entities. Okay, so this is another paper. I can show a demo also. Uh, yeah, we have some that. Okay, so here this was mostly majorly using logs, and it is leveraging LLM to get various insights from the log data. So first, the way the pipeline works, so we have log data dump coming in, there's some pre-processing done, and then once pre-processing has been done, there might be scenarios where a log line might be spread across multiple lines, so multiple log lines are combined. That's next step. And once this is done, templatization, which is basically clustering of these log lines, is performed. And now that we have templates, the groups or the clusters from these logs, we can further figure out whether the, the log lines present in each cluster, what kind of problems they represent, right? Is it there is this concept called golden signals. So these are basically these 6 types of signals which a log line can have. If the log line represent error, does it represent traffic issue, does it represent saturation issue, availability issue, right, latency issue, or is it just informational log line. So if we can classify a log line, what kind of a golden signal it represents, we can use it more effectively, right? If we know that all the log lines in this particular log dump are saying saturation, right? So there is a saturation issue going on in the system. Or if I know that, okay, initially there is a saturation issue, which is then finally I see latency issues, right? So probably saturation is leading to latency issues. So depending on what kind of golden signals are present in the log dump, we can figure out how the problem is manifesting. And similarly, we also have a fault classification, which is basically what are the various categories, right? Is this application fault, IO fault, network fault, authentication fault, or device fault? So that, and then we also figure out what is the symptom, is there some symptom present, right? This error occurred due to this problem. So maybe there's the symptom present, or is there a is there a cause present, right? Is there a cause in the log line, right? Can we highlight these portions, right? There's a symptom, there is a cause. Can we highlight the error codes, because there are so many log lines, right? Just figuring out what are the error codes is not easy. So can we highlight the error codes? Can we highlight the debug labels? All of that can really help the site reliability engineers. So eventually, once all this insights has been extracted, a report gets generated. I can show a demo of this one. So you will see that maybe I can show a demo that will be. Okay, so in the interest of time, I'll not rerun it again. I have run it once. So we have uploaded a log file here. It has around 426K log line, right? And these are the number of unique tokens. And if you see, these are the various templates which we have mined, right? So for example, with global, this is star, right? And we also have that these are the golden signals. So let's say I can figure out, let's say, latency issue, right? So operation timed out in method call, operation timed out in method call, service failure on invoke, timed out, right? All of these says there are latency issues. These log lines correspond to latency issues. And then I can also, is there a saturation issue? Yeah. So not enough memory, right? So this says there is a not enough has failed for the following region, not enough memory. That means the saturation issue is going on somewhere. And so this is how a summary of all the data, all the log lines is presented, right? So we get all the templates, templates are around 40 in number, and the number of log lines were 426k, which is a huge reduction in the volume, right? I just have to look at the 40 templates rather than looking at the entire 426k log lines. And then what happens once you have, I can also see the for each this is per hour time window, right? In 1 hour, how many number of log lines are of type, let's say, error, and of type availability, of type latency. So I can see that there are more blue happening, then there are more uh, then there are more reds happening later, right? So maybe there is availability issues are leading to errors, right? So some we can deduce from this pattern that what are the cascading effects, right? And then we also create a causal graph, which is basically, see, errors always propagate. There's problem in in one service can lead to problem in other service. And when you are getting this dump of logs, you are not getting separate, like the service A log, service B log. You have all the components log dump on you. Now, how do you figure out, right, which error is causing which other error? So can we have a dependency graph, a causal relationship among them? So here, if you see, we say this template ID 29, which is basically saying there's a session, there's a method, there's this blocked due to operation timed out in method call, right? And this issue is causing this particular issue, right? There's a connection broke, right? So we can see that this relationship can really help in drilling down what are the what are could be the potential root causes. And finally, we present a summary of this entire graph, because this again might be hard to read for a site reliability engineer. So there is a summary which says that these are the different nodes, and this is cause and effect, and maybe this is the important one which is causing lot of other errors, other problems. Okay, so with that, let me go back. And this is another recent work. I'm just giving an overview of the recent work so that this can give us an idea, give us ideas for the future work, right? And this is using LLM, right? So template mining, how do we do effectively using LLMs? So what they are saying that given a dump of logs, maybe not many log lines, let's say these are the 4 log lines, they first create a fixed depth tree, which is basically based on the number of tokens in these log lines. There is a length 3 that goes to one group, right? Length 4 another group, length 5 other group. And once they have this, they they keep an existing what are the already templates which available with the system. Are these new log lines mapping to these existing templates? So they figure out if there is a mapping template, nothing has to be done, right? Because there is already template existing for this particular new log line. But if not, then we all the unmatched log lines, for there are no templates, so they use those unmatched log lines to and then figure out more templates, right? So it's basically doing online learning, right? As in when log lines are coming, I need to figure out templates. Why? Because I want to cluster the log lines, and once I cluster, I can get the insights very easily. So these unmatched log lines, they pass through the large through a large language model, but they don't pass all the log lines. They select based on similarity. So there is a retrieval augmented generation, which is basically uh, parsing the only the log lines which are passing only the log lines which are similar to each other, so that it becomes easy for the LLM to generate templates. And then there is and the self-reflection which is being used nowadays for correcting itself, right? LLMs are using self-reflection loop to fix the problem, right? So iteratively it goes over, is this template correct? If not, then it tries again. And that way it gets new templates, and these new templates are again put back in the template memory, and then this is how the system works. Okay. So this is what just using the logs. Now, but what we have been saying, right? Multimodal A multimodal is important because there are problems which are seen in one data may not be seen in other data. So we should be looking all the data modalities together rather than in silos. So here is again just to recap, right? We have metrics, we have logs, we have traces, right? And and in this, let's say there is a service failure may cause CPU high, there could be error logs, and there could be trace latency spikes. All of these might happen simultaneously. And so why should we do multimodal, right? Because of two reasons. One is failure or the outages or the incident need not just manifest in one of the modality, right? They could be present across different modalities. So if we want to cover all the error scenario, all the failure scenarios, or a comprehensive coverage, then we should be looking at all the modalities together. For example, sometimes errors only will be seen in logs, sometimes problem will be seen in traces, maybe in both or not, right? So all of the combinations are possible. So we should be looking all the modalities together so that all the failure scenarios can be captured. And this is also important for a root cause. So let's say some faults as a memory leak may only appear in metrics, so we need to have metrics, and we just logs will not be sufficient to figure out what is the root cause. So all the combining all the modalities together improves the coverage of the root cause. And it has been shown empirically that multimodality is important for a robust diagnosis of an issue and finally finding the root cause of the issue. Now, how do we combine? That is the how do we combine these three different modalities is the main challenge. Because why? Because they come in a different format, right? Traces are basically graphs, logs are text or semi-structured text, right? And metrics are numbers. They come in different scale and they come from a different time, right? Because they are coming from different components, and all of these components are not aligned uh, on time. So there may be scale differences in time, all of that can happen. So how do we effectively combine these different data modality to finally figure out, let's say, the root cause or anomalies, right? So here in this example, if you see, right, there is a response time high or there are errors. You also see that there is a problem in the metrics also, right? So logs are also showing error messages, trace is also emitting problems, while metrics are also showing issues. This is just one more example we have, right? Here, let's say request is going from S1 to S2 to S3 to S4, right? Now, let's say S1 goes down, right? Because there's a problem in S1, this response time goes up. Because this response time is going up, this also goes up, and this also goes up. So the problem is shown in all this in this trace, right? Now trace is showing the issue, but there is a problem. There is a log line which also has an error message that S3 to S7, this service refused. This connection has been refused. And similarly, there's some symptoms in metrics also present, right? There's net out has gone down because the service has gone down, so there's not net out, right? Maybe memory CPU utilization has gone down, or the memory utilization might be some issue in the memory utilization, right? So the point I want to convey that all these modalities can exhibit the symptoms of an issue. So we should look at all these modalities together to finally comprehend or finally diagnose the problem effectively. So here are some more examples, right? This is from one of the popular data set where we have there's a failure of QR code. This is shown in memory. System stuff is again memory issue. Login failure. We have logs showing errors. Traces also showing error. File not found is shown only in traces, right? So all of these says that there's different issues or different failures are present in different are exhibited by different modalities. So maybe we should look at all the modalities together so that we can have a comprehensive coverage of all the failure scenarios. Okay, so I think I can skip these. There are more examples of why we need multimodal, but yeah, here we go. Yeah. So how can we fuse these different modalities together? So there are different fusion strategy. One is we can first this is called early fusion, right? We can do the data fusion early and then learn one model, right? And then finally, based on the joint representation, we can decide what is the issue in the system, right? Now, next representation is you can have is intermediate. It's called intermediate fusion, which is basically you fuse two modalities together, let's say, and learn one model on that one, and then you fuse the third modalities after you learn from these two modalities to be there are two models here, right? And then finally have a decision. The third type of fusion is called late fusion, which is basically you're learning from individual modalities separately, and then you are using aggregating these learnings finally to make a decision. So there are three different models learned here. Okay, so usually the first two are more popular. Even in fact, early fusion is the most popular one because it leverages the the complementary information present across these three different modalities, right? So that's why early fusion is more popular, and intermediate fusion people have not tried much. Most of the papers have used early fusion. So this is how we can do the early fusion, right? One way could be metrics and traces. We can say logs we are text in nature, right? The semi-structured text.
கேட்டாங்க சரி நான் அந்த டீடைல்ஸ் அதுக்கு தான் உங்கள்கிட்ட ப்ரௌசர் இது கேட்டேன். அப்புறம் நானே தேடி எடுத்துட்டேன் சார். அப்புறம் அவங்களுக்கு அதெல்லாம் அனுப்பிச்சு விட்டுட்டேன்.
Sorry, can you go on mute? Yeah. Okay, so logs we're saying they are can be embedded by an LLM, or we can have a log tailored LLM, right? We can get log embeddings, and then we can get, in fact, log metrics can also be embedded through LLM. So metrics can be embed metrics through LLM also, and can be embed traces also through LLM. All of these, once we get representation of metrics, traces, and log using LLM, we can fuse them together and learn a model to do, let's say, anomaly detection, root cause localization, or fault localization, all of that. So so the LLMs are being used to fuse the data together. Another approach is can we use graph, right? We know, can we use graph-based models? We know that the graph is naturally occurring in this data. We have service dependency graph, or we have traces. Traces are also graph. So can we use graph based models to fuse these data modalities together, right? So people have started with a spatio-temporal graph convolutional network, STGCN. STGCN came into picture in the traffic data. Let's say you have you have a road network of a city. So a road segment is an edge, and every intersection is a node, right? So we can create a graph out of the road networks. So they wanted to learn the traffic prediction. Can we predict traffic effectively on each edge segment, on each edge, so that better planning can be done for traffic, right? So similarly here also we can say that every service is anyway node, and there are these edges connecting these services. There are dependency relationship, which service is calling which other service. So I have this graph, and then what I say, okay, each service is emitting logs, each services also have the metrics associated with it. So maybe I can have node attributes. The logs and metrics could be the node attributes, and then edges are basically my dependency edges, right? And I can learn, and then using STGCN, I can learn a representation of this spatio-temporal data. We know that there is a spatial aspect which is coming from the topology, and there is a temporal aspect which is basically your metrics and logs. So, and then transformers have been so popular in NLP domain, and same transformer then people started using for graphs also. So can we use graph transformer network to effectively fuse these data modalities together? So GTNs have been popular, and then what does GTN do? They can find these different types of relationships, such as we know that because of log type A spikes, there's a metric B changes, so on and so forth, right? So graph transformer networks are being used to jointly to fuse these different modalities. Then graph attention networks, again different type of learning a graph, so that is also being used to fuse these different modalities together. So graph based models have been popular for fusing these different modalities together. Yeah, and okay, and how the time series being, so we need to encode the time series also, right? The matrix is a time series, so people have been using so similarly we have, let's say we have transformers in NLP domain, we have transformers for graph domain, and then people have started having transformers for time series domain. So there have been plenty of papers around time series transformers, informer, autoformer. There are a lot of these papers which are using transformer architecture to encode these time series, and that encoding can further be used for the tasks such as time series forecasting. All of that, right? So, yeah, so I will talk about a few recent papers which are doing this multimodal fusion, right? And I think I can end after that. So, this is one of the earlier paper called Fusion, and this is where they are in this paper they are combining all these three different modalities using graph transformer network. So how do they do? So they convert every all the modalities to time series, and we have said we already discussed how to convert each modality to a time series, right? Metrics are anyway time series, logs can be converted to time series, traces can be converted to time series, right? And so they treat each time series as a channel, and based on the mutual information between two channels, two time series, they figure out whether there is an edge or not, right? So they create this time series, um, and using the time series, they create this graph, heterogeneous graph, which is basically a node could be a metric, a node could be a log, a node could be a trace, right? So all of that, there are different types of nodes, and there are these different types of edges. Okay, and once they have converted this data into a graph format, they apply graph transformer network to further. So what does graph transformer network help? It basically gets gives them the enriched in a latent correlation present in the graph, right? So it can give you the relationships which do not exist but are important. So it can give all those relationships. Finally, they also do graph attention network, and finally they feed all of these representation to a GRU. So they have, let's say for each window there is one graph. So there's a stream of graph, and they feed it to a gated recurrent unit, GRU. And final representation is used to classify whether there is a problem or not, there is an anomaly or not. This is how their pipeline looks like. Okay, we don't have much time. Maybe this is the one. I will cover one more paper and we can end it. So this is how their pipeline looks like. So they have multimodal data serialization. So that is the first thing everybody has to do. So they create this time series, they create a graph, and then they do graph transform network, graph attention network, and finally get a recurrent unit to figure out whether there is a problem or not. The final representation is used. So there are plenty of these papers along this line where they're using graph to fuse these different modalities together. I'll go through maybe one more paper. Yeah, this is our paper. Yeah, I think this is I should be kept. So with graphs are being used, but then again, if you go with graphs, right, for every data we have to learn that graph neural network, right? Can we generalize? So LLMs are good at generalization. So that's why people started exploring these large language models for embedding this multimodal data, right? Can we fuse this multimodal data using these large language models? Okay, so yeah, so one of the first paper was where they fine tuned GPT-3 on logs, and they use GPT-3 for log anomaly detection. And so I can give one more paper. I can skip this one. I can talk about this one. Okay, so in this paper, what they are saying that can we use large language models to locate the root cause using these different modalities. Okay. So let's say this is your software system. You have this telemetry, this is these traces, and what we know that the problem has occurred in the system. Let's say a failure has occurred. A, there was a failure observed in system X. Please identify the root cause. So this is the time the failure has occurred, and we need to figure out the root cause component and what is the root cause region, right? So what they do is, so for this duration, let's say 9 a.m. to 9:30 a.m., half an hour duration, they get all the metrics, logs and traces, and now this is huge volume of data, right? LLMs have limited context window. You cannot feed all of this data to LLMs. So what they do, they have to compress this data, right? This is called context engineering. So basically, the context we give to LLM should be fitted in that context window. So what they do is, so they and LLM may not be able to understand metrics, right? May not be able to understand traces because LLMs understand text. So what they do, so they first find anomalies, metric anomaly, log anomaly, traces anomaly, and these anomalies they actually summarize in the form of text. Let's say metric CPU utilization showing issue, they will summarize that CPU utilization has gone up, and this is how the text will look like, right? So metric issues, metric anomalies will also be translated, converted to text. Log anomalies are anyway in the textual format. Traces anomalies also converted to text format. Now with this, again, the number of anomalies may be too much, so they further do summarization on these anomalies to finally compress, and then this compressed these compressed anomalies are then given to the large language model, and with this query that this is the failure has occurred, please find me the root cause in the root cause region, right? So they have used and they have given this data for, they have created this data actually. So there are 335 records they have created, and anybody can use this data to benchmark their system, and they can propose a new system based on this data. Okay, so I think, yeah, this one I can cover last. Okay, so what happens? I talked about earlier, right, that there is an alert storm. There's a huge volume of alerts. It becomes difficult for a site reliability engineers to diagnose issue. So alert grouping is a common thing done. So now here, if you see, this is how typically system works, right? So we have logs, traces, metrics. Okay, these are the components coming in. There will be these alerts. There is a massive alerts which are being notified to this all call engineer, but then it becomes difficult for him to figure out the issue, diagnose the issue. So what he usually done is these alerts are aggregated, basically grouping is done, and then the the on-call engineer or the site reliability engineer can figure out, he can look at individual group and then mitigate the issue. So this is how it goes in a typical system. So this alert grouping is a very important problem, and a lot of work has been done. Many research papers have come in alert grouping, and this is one of the recent paper where they are using LLM to do the grouping. So can we do the grouping using the existing LLMs, right? So now the first thing, these alerts are huge. So if I ask LLM, okay, are these two alerts, can they group together? Can they group together? There are many LLM calls, and then the volume is also huge. I cannot put all the alerts together in the context window of an LLM. So that is again a problem. So what can I do? So what these guys have done something smart is, so they first figure out based on certain correlations, right, which are the similar alerts. So let's say they do two types of correlation. One is temporal correlation, spatial relation, right? So if the alerts are coming from, let's say, A depends on B, alert are coming from A and B, then maybe these two are coming from the same issue because they are being used to in the sequence, right? So they use spatial and temporal relationship to group these alerts, and let's say the alerts which have high similarity score, they say okay, these should anyway be, these two alerts are similar, they should be put in one group. These other two alerts are similar, they should be put in another group. That they do. And the alerts which needs further testing, there is negative similarity score, which group they should be put, is what they are doing through LLM. So this is what the LLM gets. So it gets these two alerts which are not similar to each other, right? And then what they have done, they actually fine tune an LLM on this similar pairs and non-similar pairs of alerts. And this fine-tuned LLM is then further used to figure out whether these two alerts are similar or not. Right? And there is something called SOP, which is available with each alert type. So they also use these SOP to figure out whether two alerts are same or not. Okay, with that, I think I can conclude. So main summary of this entire talk is basically multimodal fusion of this data. The observability data is very important because they have complementary signals. So we should all the methods which are leveraging this multimodal data are going to be important, right? And now this graph transformer have become popular. So using graph we can embed this data, and using LLM also we can embed the multimodal data, right? And so there is actually all of these are recent papers. Open source code is available for these papers. The data is available, and there is a lot more work is here for root cause analysis, right? And basically, multimodal embedding is key to next generation observability intelligence. That is the main key away of this presentation. With that, let me conclude. Thank you for listening. Yeah, that's all from my side. Thank you.
Okay, so then thank you, madam, for your nice talk and more information. I hope that our participant will enjoy and get lot of information for their upcoming development. They will be more useful in their areas and their studies and their research and all. So thank you very much for being a part of this FDP program and deliver a talk. And I will start the next sessions. Before that, I would like to many thanks to our speaker. Thank you very much.
Thank you. Yeah, thanks for having me here. Thank you so much.
Oh, thank you.
Thank you. Yeah.
So participants will start the next session soon.
I think Dr. Singh has already joined. Yeah. Let me check.
Once again, just one request I want to put.
Hello.
Okay, speaker already have left. You can start.
Hello. Dr. Ansuman, can you hear me? Dr. Biswas?
Yeah, I can hear you. Dr. Singh, thank you for joining. I'll just introduce you to the participants. So good evening, participants. I hope the first talk was informative, and so we're going to start our next talk right now. So am I audible, everyone?
Yes.
Anshuman, I'm audible, right?
Yes, you are audible. You can go ahead.
Okay, great. So basically, right now we have with us Professor Keshav Singh, and he's a very accomplished researcher in signal processing and communications. I'll just give a brief introduction about Dr. Keshav Singh. So Keshav Singh, who is a senior member of IEEE, he received a PhD degree in communication engineering from National Central University, Taiwan in 2015. He is currently an associate professor with the Institute of Communication Engineering in NSYSU, Taiwan, National Sun Yat-sen University. He's also an adjunct professor with Memorial University, Canada. And prior to this, he held the position of research scientist with the Institute for Digital Communications in University of Edinburgh. And he was also associated with University College Dublin, Ireland, as a research fellow. He currently leads research in the domain of first generation wireless communication, particularly related to artificial intelligence and machine learning. And he has chaired several international IEEE conferences, flagship conferences like ICC, Globecom, WCC, and many more. And he is currently serving as a editor in several flagship and high impact factor transactions, IEEE transactions and journals. And he has also previously served as leading guest editors in IEEE transaction and green communication and networking. So with that, I would like to welcome you, Dr. Keshav Singh. So basically, this is the fifth day. Today is the fifth day of our workshop. Today is the fifth day of our workshop, and the participants are from variety domains, mainly from computer science in engineering and electronics and communication engineering. But there are also other faculties and research scholars from mechanical and civil. Over the last 4 days and one session today, they have gained a lot of expertise and knowledge on high performance computing, and I'm sure they're going to enjoy your session as well. So without taking much longer, I hand over the mic to you, Dr. Singh. So over to you.
Okay, thank you, Dr. Vishwas, for your nice introduction. Okay, so first let me share my screen. Okay, so can you see my slide?
Yes, it's visible.
Okay,
yes.
Okay. Hello, everyone. Good evening. Okay, so in my talk, I will mainly focus on resource allocation. So here we have two approaches. So one is through conventional optimization, another is now kind of new upcoming technology like machine learning. So here in today talk and all tomorrow, so I will mainly consider these three general papers. So first one is exploring the impact of RIS scattering on NOMA-enabled integrated sensing and backscatter communication. So recently submitted in IEEE transaction on cognitive communication and network. This work done by one of my second year PhD students. And next two are based on the machine learning. Again, this one is resource allocation. One from throughput maximization, and another is from green perspective, where we focus on power minimization. And in second and third work, we used federated learning along with the conventional method in order to optimize the resources. So today, in today talk, we will mainly focus on optimization part, so that this will be kind of, it will create the platform for tomorrow talk. Yeah, so this work done by my second year PhD student, Rojit. And yes, we can find several works on, especially on this backscatter based communication. Now the problem with backscatter is it will, you can say, propagate in a 360. So it will require more energy. So here we integrate RIS scattered, backscatter, RIS scattered, backscatter based communication. And here it will require less energy. So since we are using RIS, so it will just divert the modulated signal in a particular angle. So let's see. This is a main outline of today talk, introduction, and then a contribution with respect to the some previous works. Then consider framework, and we will focus on this problem formulation, and we proposed and provide the proposed solution that will be based on some kind of methods, approximation methods such as a fractional programming or alternating method, direction method for multipliers and HTP methods, and then we propose the iterative algorithm in order to get these solutions. So, and then finally, we will compare with some other baseline algorithms such as HTMA or this UMA, and we will see the trade-off between the communication and this target or tag detections. So why we go for this kind of technology? So as we know that day by day the IoT devices are growing very fast, along with the advancement of the technology or new applications. So according to Ericsson, by 2020-30, per month required data rate will reach up to 5,000 plus exabytes. So it will be kind of explosive data requirement in 6G. So, and the another challenge is deployment of this kind of IoT at a larger scale that will require more energy, as well as the I mean the major energy. So here we need to find some way to make this system more energy efficient, as well as along with the spectral efficient. So here you can say that need for real-time environment sensing. So here nowadays the sensing, integrated sensing and communication has become a very hot topic. So where we along with serving the solar user, we also want to detect the sensing part. So in a real scenario, so for example, in case of automotive drive vehicular communications, or maybe also in a medical sector, or like also in a marines, where we can explore this sensing and communication jointly. So here in this work we integrate the integrated sensing and communication along with the backscatter communication. So this one is this will be very unique work with respect to all the existing, and main reason is that because here we are using RFID based passive tag, which will modulate the sensing signal along with the communication, and it requires very less energy. So so here we can see some applications. So here we have this autonomous driving, so where we can serve the users as well as detect the target. So here we have communication and sensing together. So let's see, here we have RIS scattered. So here, this RIS scatter will help in radiating the signal in a particular direction, and therefore it will require very less power compared to the existing backscatter communications. So here, okay, this is another example you can see. So for example, here we have uplink scenario. So we have this traffic light. This is a base station. So it's directing the traffic signal, communicating with this one traffic signal along with the detecting the vehicles. So here the main challenge with the existing integrated sensing and communication is the limit. So here limit is just a range, you can say 5 to 8 meters. So and second is the radiation of this power, radiate the power in a 360, and due to because it can't direct to a particular one direction. So if we integrate with RIS, so then here it will radiate in a particular direction, and therefore it will also extend the range, communication range for both tag detection as well as the communications. Another is interference from backscatter tags to the users. So this one is another hurdle, and but due to RIS, now we just radiate in a particular direction, so interference will be also very less. So here you can see why we are using this RIS scatter to enhance the backscatter communication range as well as signal strength and direction of communication, and also the passive device, so it will consume less power, and due to that it will have huge you can say application, especially from IoT perspective. So here it enhanced the sensing and backscatter range up to 50 meters. So unlike the conventional where we have a range up to below 10 meter, and also it require very less power for sensing as well as the communication. Now here, in case of conventional, unlike conventional, in case of this joint sensing and backscatter based communication, the sensing will not depend on the size of the object. So it will depend on the antenna and the RIS elements. So just we can increase the RIS elements. So then the sensing performance will improve, or increase the antenna and the base stations. And also we can reduce the interference, unlike the conventional framework. So here, by optimizing the phase shift, we can also control the interference. So if we compare with some conventional methods, for example, here we have considered some latest paper, like first one published in 2024, second one 2025, again 23, 25, 24, and 24. So here you can see the here this is a first one is a conventional one, integrated sensing and communication, and the sensing matrix was SNR or CRB. And also here range is 50 meters. Okay, so no backscatter. Now here the power consumption will be very high, and also the interference. And also here range is 50 meters. But here RIS assisted sensing sensing is done at the base station, not at RIS. So the second one is they consider multiple backscatter tag, but with single user, and here range is sensing range is 3 meters, and BC range in the first case it was nil. Here we have a 12 meter. Again third we can see here range is 5 meter and 10 meter. Fourth again range is 5 meter, 5 meter, and fifth one here we can say just focus on the base station range, 50 meter, not a sensing range. So 6 sensing, so they have joint and communication based on this backscatter 6 meter, 6 meter. But here, when we use the RIS, you can say RIS. In that case, here you can see we have here we have used CRB for sensing as a key matrix. So here the sensing range reaches up to 50 meter, as well as the communication range reaches up to 50 meter. So we have huge advantage in terms of coverage range, in terms of energy saving. So this is a very unique compared to the existing works. So this is a key contribution, or you can say, I mean the key component of this work. So here we propose novel RIS scattered empowered NOMA IJAC backscatter based framework. And for sensing perspective, here we have used CRB constants. We have included this one. So in fact, we can take a signal power in terms of SNR. CRB is another key matrix or detection probability, or maybe also the now sensing rate nowadays we are considering. And since then we have formulated the rate maximization problem under the various set of constants. The problem is non-convex due to unit modulus, coupling of variables, and due to some other non-convexity of the constants. So here we adopted fractional programming, majorization, minimization methods, along with alternating direction methods for multipliers and SDP, semi-definite programming methods, in order to transform the problem into convex one. Now, if we see, because here we are using approximation, so the optimal solution will be near solution or local solution, and sometimes if the solution, I mean the solution can streamline this, obtained solution will become wide. So here we can adopt the machine learning instead of going for so much, applying so much method to get the near optimal solution. We can directly apply the machine learning methods. So here maybe let's say federated learning or multi-agent methods, and then get the solution. That will be always optimal. So from communication perspective, so machine learning is kind of you can say black box. We have just give the input and define certain parameters, and we will get the output. So that will give the optimal solution. So in tomorrow talk, that's why this one is like a framework for tomorrow talk. So we will see how to apply federated learning, especially in the case of NTN communication, so terrestrial and non-terrestrial communication. And here we demonstrated the scalability. So due to this RIS scattered, so we can increase the range up to 50 meter. Again, this 50 meter depends on the how many RIS elements we are using. If you increase the RIS elements, let's say 256 or 1024 or even higher, so still we can maybe increase up to 75, 100 meters or even higher. It depends on the RIS, the elements. And through simulation, we have shown the trade-off between this sensing accuracy as well as the communication efficiency. So here, this is a system model. Here we have considered dual functional base stations, which serve multiple key number of downlink users, along with detecting the tag signals, or you can say these target tag signals. So which is let's say IoT device, that one having embedded with this RIS. Now, so here you can say SM is a transmitted signal from base station or this is a superimposed signal. So we have K users. So this is a precoder for the cellular user, and this is for the tag WS W0. Or we can write in a more compact way in this second equation. Now, so the backscatter, the receive signal will be at the base station will be given by this equation WR M. Sorry, this is a backscatter. Okay, so we have alpha t time t. This is a RCR. This is a radar. This is related to the alpha t is reflect the quality of echo back of the signal. If alpha t equal to 1, so that means perfectly echo back to the base station. D is the modulated signal. Eta is efficiency, modulation efficiency of tag. This is a channel. Phi is a phase shift from RAS tag to the base station. So here, and this is noise. So we can define the gamma t. So this one is receive SNR at the base station, where U is, you can say this is a receive beamforming for a modulated signal, since the base station has a multiple antenna. And here we define the rest of variable. Here you can see this is a phase shift unit modulus phase shift. Okay, now this is a communication model. So this is a receive signal at the jth user. So that this will be given by this one. So the first part, so we have we can define. We can also have the direct link along with. So the each user will receive. If you see here, the system model, user will receive signal from the base station along with the this IoT devices or this target, or you can say tag devices it will receive. So here we have this. So this one is from tag to this one, and this is from base station. This is for target one, and this is noise at the jth downlink user, and this will be the interference. So sorry, this is a SNR. So this term is interference, and this one is a reflected back. I mean from the target. So this will be communication SNR. Here we are applying NOMA. So just apply the NOMA principle. For that we can say we have this scenario where this one you can either in ascending or descending order based on the channel condition. So we can apply this NOMA condition. So in order to detect the tag signals, here we adopted CRB. So this one work as you can say benchmark to evaluate the efficiency of the practical estimators. So here in this case, in case of CRB, we have the one unknown parameter theta, that is a direction of arrival. So from tag to the base station. So here this is a receive signal at the dual functional base station. After modulation will be given by this one. So we have seen this one, and this is a more compact form in a matrix form. And then here we define the Fisher matrix. This is from this YR we define the Fisher matrix, and then CRP. So the other parameters are here. And here we can see this alpha will. So here we have two variable. You can say theta and alpha is depends on this alpha t RCS parameters. Now here our task is to maximize the total sum rate under the power constants along with QS of each user and the SNR of the tag along with unit modulus constants, and this is a CRB constants. So this is you can say the this should be, we put the threshold, this CRV should be less than or equal to zeta. So here you can say now, so if you see this problem is non-convex due to multiple logarithmic terms. So also here the variable appear in numerator and denominator, and also here due to C2, C3 unit modulus and C5. So due to this, the problem is, you can see it's not easy, or we don't have any very standard method to get this solution. So here we need to do several level of approximations before getting this solution, and the obtained solution will be only local optimal or near optimal solution. So here the machine learning will be much suitable in order to get the very efficient, or you can say optimal solution. So here first we go for this conventional method, and then tomorrow we will see how we can apply this federated learning in order to get the solution, and we will compare with this conventional method. So first of all, we transform this objective function, this approximate this objective function. Here you can see we introduce some auxiliary variable alpha and beta, and we approximated in this form. Okay, so this one is a objective function. So for detail, this paper is just submitted. So next week it will be online on Tech Archive. You can download and see the details. Okay, so here we have rewrite. The rewrite in a more compact form. So this the objective function. So finally we have this one. We redefine W in this form, A in this form, and Wi again this Ti and W. Similarly, we have some other variables. Now the transform problem will be this one. So, but still this one is still very tough to get the solution. So what we did, so unit modulus constant and 25 phi, we introduced this one in an objective function, and we transform this one into in this form. So maximizing function f0 is nothing but minimizing minus f0. So here we converted in this, minimizing this one, and we incorporated this one here, the 25 I and unit modulus constant here, and we introduce a new parameter rho y that will that's value will be between 0 and 1. And then here this problem, we can solve this problem by using ADMM method. So that means here we fix some parameter and obtain another parameters. For example, here we can update alpha and beta for giving rest of parameters. Once we obtain alpha and beta, then we can update the u. So this one is nothing but we are doing the maximizing the SNR of the tag under these constants. So finally we will have this u, optimal u. Similarly, once we have alpha, beta, and u, we can solve for j and f. So just we ignore some constant which are independent of this, and then we will have this one. And then update w. So for rest of parameters, we can update w again. This is a non-convex, so we need to convert into transform this one. And again, this one sum of constant here are non-convex. So we apply SDP. We transform into this one into SOCP second order cone form. So now after this, so the problem will become convex, and we can get the optimal W. Now, and then so last is to find the phase shift, and this one play the very important role in order to detect the tag, or you can say target. So this is a phase shift. This is our optimization. So rest of you can just ignore rest of constants which are independent of this phase shift. And this problem again, after doing some approximations, so here it requires several level of approximation. For example, here we introduce another zeta variable which is equivalent to phi, and then convex, I mean surrogative function in order to transform this one into a convex one. So and finally we will get this phi and this zeta optimal for given fixed dual variables. And then we can update this dual variable by these two equations. Once we have this phi theta and these functions, then update these dual variables. So this is you can say algorithms. So here we have we need to give the input, define the output will be W and phi. This is a two major output, and other I mean the ugly variable that will be based on this initial parameters. Firstly, we initialize W and phi using RCG methods. So this is also well-known methods, and then we apply this ADMM. So we fix other parameter. For example, here we update alpha j for using this one, then beta j, update u, and similarly update j and f, w, phi, zeta, and the other parameter. Now here 12, this is a questionable. Row 1 is, let's say, we are considering let's say 80% this value, and this one the optimal, I mean the best solution. So in fact, I discussed with my PhD student to find why we are getting at this, I mean getting the optimal solution at this point. So hopefully I will get the answer of this one in next week. First he will simulate and he will cross verify this value. But in some existing literature, they also consider this one without giving the region. Okay. So we have some interesting results. So there are several results. We'll see. So these are the parameter settings. We have, let's say, carrier frequency. Eta is this one. The transmit power, bandwidth, noise, and we have T 270K, and here we compare with various benchmark scheme like conventional IJAC, integrated sensing and communication, that is a non-bicameral communication, RIS assisted IJAC, and then this is integrated sensing and backscatter based communication with single tag. Okay. And this is a proposed one, but for I mean with OMA and SDMA, and also we have compared symbiotic radio. So here first figure is showing the convergence of the proposed algorithm. So here we can see under a particular setting, so with respect to various powers, so here you can see the proposed algorithm will require very less number of iterations, so hardly 20 iterations in a convergence. So it's a very fast, and the complexity will be much lower than the exhaustive one. So here, this is a beam pattern of integrated sensing and backscatter based communication. So here you can see this is a tag, this is a users, and this one is the base station. So this one, it's create the beam towards the these users, and we also have this directional, you can say this beam for the target. Now we have one drawback, this one, so we are still working on. So if this tag falls in line with these users, then what will happen? There will be interference, and then performance of this tag detection will be affected from the communication, and also this performance of several users. But here we consider, let's say, in a tag is in a particular directions, and there is no overlap. So here, in this case, we can have the very fine beam for users as well as the tags. And also, this one is for single tag. We can also consider for multiple tags. So there, of course, the performance will be slightly lower, but overall the system performance will become much better. So in figure 4, here we show the impact of reflecting elements. So this is obvious when you increase the reflecting elements. So we can gain virtual diversity, and due to that, the tag rate will become better and better. So along with this, here we have shown the distance, impact of distance from a base station to tag. So here, if tag is closer to the base station, so of course it will give the slightly better performance. So here we can see 30. This is 30, and this is a 50 meter. Here we can also, when eta equal to this is a modulation efficiency, so this is a 0.6 and this is a 0.5. So by increasing modulation efficiency, we can achieve the better tag rate. Along with that, so here we can see these RAS elements. Along with RAS elements, the tag performance is improving. So that means if you want to achieve the better performance, just increase the RAS element. Okay, so in one figure we will see the comparison between perfect SIC and CSI, and as well as imperfect CSI and SIC, where this RAS element will play a very important role. So in figure 5, we have tag rate versus modulation efficiency. So this one, along with this modulation efficiency, so here we can have the better performance, or the proposed one give the better performance. Here single tag, that means no RIS, only we have a single tag. So here its performance is almost close to zero. So here we can see we have clear advantage. If you are using RIS scatter, then we can have the much better performance. Now, the next figure is here to have tag SNR requirement. This is a QS requirement of the particular tag. So here we can see, as we increase this tag requirement, so some rate, for example, in case of when tag is closer to the base station, then the performance of silver rate is improved. Okay, because here you can say tag is closer to the base station, it will use less power for the tag detection, and more power, it will allocate more power for silver. So we have a better performance, or you can say achieving the better sum rate. However, when the distance becomes 50 meters, so that means now it will use more power in order to detect the tag along with this higher QS. So it will allocate higher power, and therefore here you can say rate will silver performance will slightly decrease. Again, in figure 7, here we have compared this performance of the proposed one with OMA and SDMA. With respect to number of users, here we can see the proposed one is outperformed for all number of users here. So So again, here figure 8, here we show the sum rate, the cellular performance, and this is a base transmit power at the base station. So again, this is obvious, but here we compare with perfect CSI and SIC, with imperfect CSI and SIC and CSI. So here we will add, I think, image one curve. We need to add one curve. So here we can see that this curve is for RAS element equal to 16. Now we also need to have 64. Then we can say if we have 64, then we can achieve the same performance as like perfect CSI. So that means just by increasing the RAS element, we can have the same performance with lower RAS elements under perfect SIC CSI. Anyhow, under even in this scenario, if you see if transmit power is higher, the gap between the perfect and imperfect SIC and CSI become lower. So this one is a huge advantage over the conventional one. Again, this one is very interesting. Here, hijack with we have a different scenario. For example, sensing at the base station and also at the user, sensing at only at the user and the base station. So we have a different scenario. So here we can see if you have at with respect to RIS, this with respect to RIS. So this one is giving a better performance compared to the other scenario. For example, this one, base station transmission and with user. This one is just a minute. So first one is a symbiotic radio. Symbiotic radio. So the proposed one with symbiotic radio, here you can say it's performing much better. Where base station will treat both communication signal as well as modulated. The signal for the modulated signal just to detect the tag. So here this one is become better. But if we use the sensing and as well as modulated at a different perspective, like a base station and a cellular, then the performance will become lower. This is sum rate versus CRB, because since here we are considering CRB as a one of key performance metrics for tag detection. So here we can see if CRB, this threshold, if we are increasing, so the sum rate for the cellular will improve, because the tag will require less power, or it will, because it can compromise with some error, so it will require less power. So cellular, the base station can allocate more power in order to improve the throughput of the cellular users. So here we have a clear improvements. Also here we compare with scatter without RIS, and this is with RIS. So again with RIS is we can achieve a very high performance especially compared to the without RIS scenario. And also with in case of conventional, this only scatter. So here I think this is the last figure. So here this one is very interesting. So this is a distance of the tag from the base station. So RIS scatter tag from the base station. And here we compare with hijack, no NOMA with single tag and RISC scatter with 32 elements. So here, when we have, let's say, distance between base scatter and RISC scatter is very low, here we can say the proposed one is giving worst performance. So I think due to the initialization process, so this one will take some time to reach to the optimal value, and due to that here the performance is lower. But just after let's say 5 iteration, it start performing or outperforming the this rest of two. Now here when the RISC scatter is going far, so here the sum rate is decreasing. Sum rate of the solar systems. Why? Because solar system will now the base station will start allocating more power for detecting the tag. So therefore, it will reduce less power, or it will use less power for this solar system, and therefore here the rate for this solar will decrease. However, with the proposed model, still we can have the significant sum rate compared to this conventional and with a single tag. So I can conclude here. We propose RISC scatter, which is able to extend the range as well as maintain the reliability, and also through NOMA integration, we achieve we improve the spectral efficiency. And the CRV constants, so this one ensured the guaranteed sensing accuracy. So here we can extend this work. We can consider, let's say, multiple RISC scatter. That means multiple target you can consider. And then in order to further enhance the range support and also the multiple users. And along with, we can have the various application like in healthcare, agriculture, smart home, or smart mobility, where we can experience multiple RISC scatter with multiple users. And here, because finding the perfect channel state information will be very difficult, so we can also examine the robustness under CSI errors. Also, we can consider hardware constants. Also, quantize phase shift error. We can consider, and we can make a very robust system. So okay, so this is all about today presentations. So tomorrow we will focus on this federated based method in order to optimize the resources in terrestrial and non-terrestrial communication from both, I mean throughput maximization and power minimization. Yeah, thank you.
Okay, so thank you very much, Dr. Singh. So, let's participant, if you have any questions, query, you can ask to the professor. And, we will end this session before it. If you have any query, you can ask.
Sir?
Yes, from anyone else have any questions?
Some faculties are asking my USPA is not.
Hello.
Hello. Srinivasan, I think someone want to ask some questions. Anybody? Please ask if you have any questions on the topic, or you have any doubt, you can discuss with our speaker today. No question? Okay. So I think there is no questions from anybody.
So anyway, if anyone has questions, so they can write email or they can just check my paper and they can find my email there and email me. I will be very happy to answer their question.
Definitely. Okay. So, okay, guys. So, if you have any questions, if you have any queries, you can directly write an email to our speaker. Then he will be very happy to give an answer or give you the reply to your mail. So, thank you, then, Dr. Singh, for your nice talk and informative talk. So, I hope that all the participants will enjoy and they will utilize this information, this knowledge in their career development and their research and all. So once again, I thank to you being a part of this FDP program and for your nice talk and presentation in these sessions. And again, you have another talk for tomorrow, the last day of our FDP program. So thank you very much. So I will.
Thank you. Okay.
I will also request to Dr. Singh to please share your slides so that I will send to our and so that they
Since
can.
still this paper is not online, so
Okay.
come online, I will share. But for tomorrow talk, I will share the PPT.
Okay, thank you then.
Yeah.
Okay, fine. That's all. That's good.
Okay.
Okay. Thank you then once again.
Right.
Thank you very much.
Bye.
Okay. Bye. So participants, so thank you very much for today's sessions for joining and then sincerely listening to the sessions that is by our speaker of two sessions very nicely deliver their informations, knowledge on the various field from industry background as well as academic background. So today's session was very informative and very energetic also. So I hope all the participants may get more benefited by gathering knowledge, acquiring knowledge, and in their upcoming research and career development in future. So thanks to all of you, all the participants. So please, if you have any query, comment, and suggestions, you can put in the feedback link, feedback form. Already we have shared the feedback link to WhatsApp and also the live chat. So you can just open it up and fill it up and submit as soon as possible for attendance, today attendance, as well as feedback for the sessions. So then we'll again start sessions tomorrow. That will be the last session for this FDP program because we are in day 5 and that is end today. So now day 6 or last date of this FDP program will start tomorrow. And also I will remind to all of you that there will be an exam of tomorrow. Then this exam will be taken place the end of 3 sessions. So tomorrow we have 3 sessions. The session will start at 2 p.m. Already we have shared the details program schedule of this FDP program with all of you. So please go through it, check it once again. Then you can understand that what are the sessions topics and the time schedule as well. So again, I recall once again to all of you that tomorrow session will start 2 p.m. and we have 3 sessions and 3 talks, 2 p.m. to 3:30, then 3:30 to 5, and 5 to 6:30. We have 3 speakers for 3 individual sessions. One is from UK, and another is from IIT Indore, and another is for Taiwan. So 3 talks will be 3 talks are scheduled tomorrow from 2 p.m. to 6:30 p.m. So in the 6:30 p.m. after end of 3 talks, we will schedule an online exam around 6:30 p.m., 6:35, 6:40, and the exam will start. So we'll send you the exam link so that you can give your exam online. An MCQ type questions. We will probably take 30 minutes exam. Probably will give you 30 questions, 30 MCQ questions, and then we'll give you 30 minutes for the exam. 6:30 to 7 p.m. the exam will be going on. So after that you have to submit it in 7 p.m. Then after that we will conclude the whole program. I will take overall feedback from everyone, suggestions from everyone, and then finally we will conclude the whole sessions. So that is the today's schedule. So I will request to all the participants, all of you please join timely and also be an active whole sessions, because today is I expect that today is holidays because Saturday, so you can easily be in full time involved in the whole program sessions. So this is the information regarding tomorrow schedule and for the exam. So I will once again remind you that based on the score of your score of the exam and the attendance, the AUTOL actually generate the certificate and issue the certificate for all of you, right? So there is an conditions in the AUTOL norms, that is the 70%, more than 70% attendance throughout the program session, and maybe more than 80% score of the exam actually minimum requires to obtain a FDP certificate. I know maybe all of you know this information. Just I repeat once again. So be careful about it and be present in the exam and properly prepare for the exam. And also I expect that all of you nicely will do this. Okay, so thank you all of you. If you have any questions, query, comment, or any suggestions, you can share with us, or else we can conclude today's session. Anyone want to say something? So any one of you have any questions, query, comment, suggestion, objection, anything else? If you have, you can share with me, or else I will conclude the session for today. Again, we will meet you tomorrow. So just I will wait for 1 minute. Just if you have any discussion, you can share your thought or your comment or your suggestion with us. Already we have shared the attendance link in WhatsApp. Please put your attendance and also your feedback by submitting the Google form. It is already been shared in the WhatsApp. So please check your WhatsApp and then open the link and submit the Google form as soon as possible. That will be included as your attendance come feedback. I will not send you separate email, right? Only we are putting the link in the WhatsApp only. So you please, all of you please take this link from the WhatsApp. Okay, then thank you very much, all of you, all the participants. Thank you very much to all of you. So we'll stop here. As actually I have mentioned, tomorrow we'll start session 2 p.m. and also 6:30 will start online exam for half an hour. MCQ type question, be prepared for that. And actively please attend tomorrow session, tomorrow 3 sessions, start with from 2 p.m. onwards. Okay, thank you very much. So I will just stop here. So I will just stop here and conclude today's session. Thank you to everyone. Have a good day. Good night.
Thank you.